In this video, we solve problem number 4 from Differential Equations quiz number 6 during the spring 2021 semester. Problem number 4 covered standard L25 IVPs with the Laplace transformation. And these are pretty basic IVPs. In another standard, we cover more advanced IVPs. Here, we only have to use partial fraction decomposition and our sort of straightforward Laplace transformations, those initial Laplace transforms that we learned and inverse transforms to solve the problem. In the other standard over IVPs, we have heavy side functions on the right-hand side. We have Dirac delta on the right-hand side. Our differential equation may have polynomial coefficients, but in this standard, we've got our first type of IVP, which is just a first application of the Laplace transformation method. And there were multiple versions of this quiz, so if you're taking my class, you may not have seen this problem, but you probably saw something similar. So anytime you're solving an IVP with the Laplace transformation, the first thing that we need to do is define our notation. So we're going to let the Laplace transform of y of t be capital Y of s, sometimes I'll call it big Y of s, just so that everybody knows what that notation means. And then after we do that, we take the Laplace transform of the differential equation. So we'll start that way. And then remember the Laplace transformation is a linear operator, so you're going to apply that to each of these terms. So we'll have 9 times the Laplace transform of y double prime minus 6 times the Laplace transform of y prime plus the Laplace transform of y equals 12 times the Laplace transform of cosine of t plus 16 times the Laplace transform of sine of t. Now to compute the Laplace transform of y double prime and y prime, we have to remember a rule, or at least look up the rule in our table of Laplace transforms for the Laplace transform of the nth derivative of a function. So if I go to my table of Laplace transforms, the one that I provide for you during your quizzes and exams, you're going to use entry number 54, which tells us that the Laplace transform of the nth derivative of f with respect to t is given by this expression on the right-hand side. Now remember what we said in class. If this is the nth derivative, there are n plus 1 terms over here. The first term starts with an s to the n factor. And then we're subtracting all the other terms, and the powers of s go down. So we start with s to the n, then we have s to the n minus 1, then s to the n minus 2, until finally we have an s to the 0. So there are no s's on that last term. And then we take each of those powers of s and we multiply by the Laplace transform of the function here, not the nth derivative, but the function f of t, which we call f of s. And as we go from left to right, we multiply by little f at 0, little f prime at 0, little f double prime at 0, with the derivative increasing as we go all the way to the end. Now this last term will be the s to the 0, which is just 1, we don't write that, times the n minus 1th derivative of f evaluated at 0. So if this is the 5th derivative, that's going to be the 4th derivative evaluated at 0. Okay, so with that in mind, here I have the nth derivative of y with respect to t, and we're taking the second derivative, so n is equal to 2. And here, n is equal to 1. So we're going to use that rule for both of those. This was entry number 54 in the table. And it says this: the Laplace transform of the nth derivative of f is s to the n times f of s minus s to the n minus 1 times little f at 0 minus s to the n minus 2 times little f prime at 0. And you keep going until you have an s to the 0 times the n minus 1th derivative at 0. And there are always n plus 1 terms on that list. So for n equals 2, I'm going to have 3 terms in that Laplace transform of y double prime. We start with an s squared, and then we multiply by the Laplace transform of y of t, which is y of s. And then we subtract s to the 1 less power, and then subtract s, or s to the 0. So we've got s squared, s to the first, and an s to the 0. Then multiplying the s to the first and the s to the 0 is little y at 0 and little y prime at 0, with the derivatives increasing as we go from left to right. So that is the Laplace transform of y double prime. Don't forget your parentheses here. All of that is multiplied by the 9. That's very important. Then we have minus 6 times the Laplace transform of y prime. Since that's the first derivative, n equals 1, so we're going to have two terms here. We start with an s to the first, and then we'll have a minus s to the 0 term. This one gets multiplied by y of s, and this one is little y at 0. Then we're adding the Laplace transform of y, which we've defined earlier to be y of s, and that equals 12 times the Laplace transform of cosine of t. Now this is cosine of kt, where k is equal to 1. From our table, we know that the Laplace transform of cosine of kt is s over s squared plus k squared. I'm not going to look it up in the table this time, but you can look up the Laplace transform of cosine of kt. It's one of the early entries in our table, and it says s over s squared plus k squared is the Laplace transform of that. Now that's one that I recommend that you memorize because we see it so often, but you don't have to memorize it. It is in the table. This is very similar, sine of kt, where k is equal to 1. Excuse me. So we'll have a k over s squared plus k squared for sine of kt. K is 1, so we'll have 1 over s squared plus 1 squared, which is, of course, just s squared plus 1. So that is the Laplace transform of our differential equation. And of course, we want to substitute the initial conditions as well. So we're told that y of 0 equals 0. So this is 0. And y prime of 0 equals -1. So that's -1. So what we have is this, after simplification, 9s squared times y of s. And then this is a -1. So it's a positive 1 times 9. So it's going to be a positive 9. And that's 0. So this turns out to be -6s times y of s. And then we have plus the y of s equals this. Now you can multiply straight across there, thinking of that as a 12 over 1 and thinking of that as a 16 over 1. So we have 12s over s squared plus 1 plus 16 over s squared plus 1. All right. So that is the Laplace transform of the differential equation with the initial conditions substituted. Now we just have to solve for y of s. Okay. So if we're here and we want to solve for y of s, I would just group these terms involving y of s on this side and then subtract that 9 from both sides. So I'm grouping these and I'm factoring out the y of s. So I'll have 9s squared minus 6s plus 1 times y of s equals the right-hand side minus that 9, because I want only the y of s terms on this side. So I'll subtract 9 from both sides, and that 9 will end up over there. Now this is easiest to compute the inverse transform of if we do a little bit of algebra first. This factors. I need the first times first product to be 9s squared. So I think I can use 3s and 3s here. If I need two numbers that multiply to give me a positive 1, and I need this term in the middle to be negative, I can use -1 times -1. Now watch this. First times first is 9s squared. Outer times outer is -3s, and inner times inner is -3s. So together that's going to give me the -6s, and the -1 times the -1 is the positive 1. So y of s is multiplied by this product, and since those are the same, you can write it as 3s minus 1 quantity squared. And on the right, since these have the same denominator, I think I will combine them. Now, if I want to get y of s by itself, I can divide both sides by 3s minus 1 quantity squared. Now, dividing by a number is the same as multiplying by 1 over that number. So just for example, if we're talking about 2, dividing both sides by 2 is the same as multiplying by 1/2, because half of something is the same as dividing it by 2. So if I want to get the y of s by itself on this side, I can divide by this. That's going to be the same as multiplying each of these terms by 1 over this. Now you could just divide by that and then multiply by the reciprocal, but you're going to end up in the same place. So after simplification, we have y of s equals this 12s plus 16 over s squared plus 1 times 3s minus 1 quantity squared minus 9 over 3s minus 1 quantity squared. Now, for this piece, I want to use partial fraction decomposition so that I will have an entry in my table or entries in my table that will allow me to find y of t. So after solving for y of s, we want to rewrite y of s so that we can compute its inverse transformation, inverse Laplace transform, using our table. Okay. And that requires partial fractions. So we'll start here. And I'm just focused on this one piece. And with that one piece, I'm going to write the appropriate form of the partial fraction decomposition for that rational expression. I've got an irreducible quadratic factor. So I'll have as plus b, because that's an irreducible quadratic factor, over s squared plus 1 there. Now this is a repeated linear factor. So I'll have two terms for that repeated linear factor. It'll be a constant over that factor plus a constant over that factor squared. And then we will multiply both sides of this equation by the original denominator. Don't want to multiply all those together because then we'd have an s minus 3 or a 3s minus 1 cubed, and we don't want that. We want the least common denominator, which is always the original denominator for these problems. I want to multiply both sides by that. When you multiply by the LCD, the denominators will all reduce. And that should be in the numerator, but I've sort of run out of space. So that's multiplying that entire term, not just the denominator there. And then we'll simplify. This reduces with this, and this reduces with that. The s squared plus 1 reduces there. One of these will reduce, and then both of those will reduce. So what we'll be left with is the original numerator, the 12s plus 6 equals as plus b times 3s minus 1 quantity squared. And then here we have c times s squared plus 1 times 3s minus 1. And then the last term is d times s squared plus 1. Okay. So we wrote the form of the partial fraction decomposition. We multiplied by the LCD and simplified. And now we've got four constants, a, b, c, and d. So that means we're going to have to choose, four values of s to find a, b, c, and d. Usually we choose the values of s that cause the factors to be 0. Now we actually only have one linear factor that is 0, or that could be 0, and that's that 3s minus 1. That's 0 when s is equal to 1/3. So I will substitute s equals 1/3 on both sides here. When s is equal to 1/3, we have 12 times 1/3. 1/3 of 12 is 4. 4 plus 6 is 10. And then over here, we'll have 1/3 times our A plus B. Oh, and if S is equal to 1/3, that's going to be 0. And since S is 1/3, that will also be 0. So we'll have C times 0 there. And then the last one, we have D times 1/3 squared, which is 1/9 plus 1. So we have 10 equals D times 1/9 plus 9/9, getting common denominator. 1 plus 9 over 9 is 10 over 9. And then to get D by itself, we'll multiply both sides by the reciprocal. So we'll have 10 over 1 times 9 over 10. Multiplying both sides by the reciprocal of that to isolate D. That's what I'm doing there. And of course, the 10s reduce, and we find that D is equal to 9. Now, because that factor was repeated, and S squared plus 1 never equals 0 in the real number system, we usually just choose 3 more values of S in order to find the A, the B, the C, or the A and the B and the C that are left. We already know what D is. So I would choose the easiest values of S first. So I'll choose S equals 0. When S equals 0, the left-hand side is 6. This is A times 0 plus B, so it's going to be B times 0 minus 1 is -1 squared, plus C times 1 times -1, plus D times 0 squared plus 1, which is 1. So we have 6 equals B minus C plus D, D, and we know that D is equal to 9. I was already starting to substitute. So if we subtract the 9 from both sides, we have 6 minus 9 is -3. So now we know that B minus C has to be 3. What I'm trying to do is I'm trying to get 3 equations and 3 unknowns, and those unknowns are the A, B, and C that we're still looking for. So we need to substitute another value for S. I'll choose S equals 1 because it's easy to evaluate expressions at S equals 1. 12 times 1 plus 6 is 12 plus 6, which is 18. And that equals A times S plus B. If S is 1, that's just going to be A plus B times 3 minus 1, that's 2, quantity squared. 2 squared is 4. And we're adding C times 1 squared plus 1, so it's going to be 1 plus 1, which is 2, and 3 minus 1, which is also 2. So we'll have 2 times 2, which is 4, plus D times 1 squared plus 1, so it's going to be D times 2. And let's see, we know that D is equal to 9. And we'll distribute that 4, or I like to distribute the 4, I think. It's a good idea. 9 times 2 is 18, so we can subtract the 18 from both sides, and we get 4A plus 4B plus 4C must equal 0. And if I divide everything by 4, that'll make it even simpler. A plus B plus C must be 0. Okay, great. So I've got 2 equations with 3 unknowns. I just need 1 more equation. So I think I will substitute S equals -1 next. When S equals -1, we'll have -12 plus 6, which is -6. This will be -A plus B times -3 minus 1. That's -4. -4 squared is 16. Then we're adding C times -1 squared plus 1. -1 times -1 is +1. 1 plus 1 is 2. So we'll have a 2 there times -3 minus 1, which is -4. Plus D times -1 squared, which is 1. 1 plus 1 is 2. Okay, now let's simplify and remember that D is equal to 9. So I'll distribute that 16. So I have 18 over here. If I subtract 18 from both sides, negative 16, negative 6, excuse me, minus 18 is going to be negative 24. And I see all of these are multiples of 8, so I think I'll just divide everything by 8. If I divide by 8, I have negative 3 here, and then a negative 2a here, and a 2b, and a minus c. So we have 3 equations and 3 unknowns for a, b, and c. The first one was negative 3 equals b minus 3. The second one was 0 equals a plus b plus c. And the third one is negative 3 equals negative 2a plus 2b minus c. So basically, you choose the value of s that will cause that factor to be 0. And then if there are 3 constants left, you choose 3 values of s to get 3 equations and 3 unknowns. And then you solve those 3 equations and 3 unknowns for your variables through whatever method you like. I like to systematically from here just eliminate one variable at a time. I see that negative c and the c here, and that is positive c and the negative c there. So if I call this equation 1 and this equation 2 and equation 3, if I add equations 1 and 2 and I add equations 2 and 3, I'll be able to eliminate c. So I think I'm going to choose a variable to eliminate. I'm choosing to eliminate c. And this is what I get when I do that. Equation 1, I'm going to write it in the reverse order. We have b minus c equals negative 3. If I add that to equation 2, that's a plus b plus c equals 0. The c's are gone, and I just end up with a plus 2b equals negative 3. Okay, that's one way to eliminate c. Now, with the second way to eliminate c, I have to use the third equation. But I can use any one of these other ones I want. Since this one has a positive c and that one has a negative c, I'll add the equations 2 and 3 to get rid of the c this time. So equation 2 looks like this. Equation 3 looks like this. And we'll have a negative a plus 3b equals negative 3. So now I've got 2 equations and 2 unknowns. Because I chose to eliminate my c, I'll call this equation 1 star and that equation 2 star. And now we're here. And the goal is to eliminate a variable from here. Well, since I have a positive a on this one and a negative a on that one, I think the easiest variable to choose to eliminate is a, because if I add those together, the a's will be gone. So we'll choose to eliminate a. We'll have 5b equals negative 6. So b equals negative 6 divided by 5. And once you know b, you can use b to find a. According to this, a is equal to, that's from equation 1 star. If we solve for a, we have a equals a negative 3 minus 2b. So that's negative 3 minus 2 times negative 6 over 5. So we have negative 3 plus 12 over 5. And negative 3 is the same as negative 15 divided by 5. So add the numerators, keep the common denominator, and you have a equals negative 3 over 5. Okay, so our a is here, our b is here, and our c, have we found c yet? I don't think we have found c. But since we know what a and b are, we can use b to find c using this, substituting into this equation. Negative 3 equals b minus c. Or b minus c equals negative 3. So that means that negative c equals negative 3 minus b. If we multiply both sides by positive or negative 1, we get 3 plus b is equal to c. So we've got 3, which is 15 over 5, plus b, which is negative 6 over 5. So c will be 15 minus 6, which is 9, divided by 5. Okay, so now you've got your A, your B, your C, and your D from multiplying or from substituting 4 values of S. The first value of S gave us D, and then we were able to come up with 3 equations and 3 unknowns and solve for A, B, and C by systematically eliminating variables. Now that we have the A, B, C, and D, we can substitute those in right here, and that's going to be the appropriate partial fraction decomposition for this piece. So remember, our goal is to find the partial fraction decomposition for Y for the purpose of being able to compute the inverse transformation. So let's keep going. Y of S was equal to AS plus B over S squared plus 1. And A was negative 3/5. So I have negative 3/5 times S plus B, which was negative 6/5 over S squared plus 1, plus C, which was 9/5 over 3S minus 1, plus D, which was 9 over 3S minus 1 quantity squared. So that's this piece right here. And then we're subtracting 9 over 3S minus 1 quantity squared, because that was part of our Y of S from before. And those are the same, but with opposite signs. So those reduce. And this turns out to be our Y of S. Now, I don't have a rule for this, but I have a rule for an S over S squared plus 1 and a constant over S squared plus 1. So I'm going to split this into 2 pieces. I'll have negative 3/5. I'll factor out that constant times S over S squared plus 1. So I've got a constant times something that I have a rule for. Here, I'll factor out the negative 6 over 5. Then I'll have a 1 left in the numerator. Over S squared plus 1, I have a rule for that. Now this one I don't have a rule for because we have a constant. We can think of the constant, we can always factor it out. We have a 1 over S minus A, and there's no constant in front of the S. So as soon as I see that constant in front of the S, I know I've got to do a little bit more algebra. So what I'll do is I will divide the denominator by 3, and that's legal as long as we also divide the numerator by 3. So what I would recommend in this case is thinking of multiplying by 1/3. Dividing this by 3 and multiplying that by 1/3 is doing the same thing to the numerator and denominator. And that's legal, and it's going to leave us with an equivalent expression. 1/3 of 9/5 is 3/5. And here, if I divide that by 3, I'll have an S, and then I'll have a negative 1/3 there. So if I want to, I can even go further and factor out that 5/3. Now these match patterns from our table. I've got a pattern for the inverse transform of S over S squared plus K squared. That's cosine of KT. And the inverse transform of K over S squared plus K squared, which turns out to be sine of KT. And the inverse transform of 1 over S minus A, which is e to the AT. So those match those patterns. Here, K squared is 1, so K is equal to 1. And here, K squared is 1. So K equals 1. In order for these patterns to match, I need a 1 in the numerator, and I have a 1 in the numerator, so I'm good there. If the constant in the numerator wasn't exactly what I needed it to be, I might have to multiply by a well-chosen 1, but in this case, I don't have to. And this last one is 1 over s minus a, and the number we're subtracting from the s is a. So that's a 1/3. So y of t is the inverse transform of all of this. So we have -3/5 times the inverse transform of this piece, which is cosine of kt with k equals 1. So cosine of t. Then we have -6/5. I don't know if I said that right last time. This is -3/5 times cosine of kt. Here's -6/5 times the inverse transform of this piece, which is sine of kt with k equals 1. So that's sine of t. And then we bring the 3/5 down and we get the inverse transform of this piece, which is e to the at, where a equals 1/3. So it's e to the 1/3 t, or if you prefer, you can call that t over 3. So that is our y of t. And that is the solution of the IVP. Now let's look at the original IVP. It's right here. If I take the first and second derivative and the function itself, and I substitute into the left-hand side and simplify, after simplification, I should get 12 times cosine of t plus 16 sine of t. Now, if I evaluate my expression at 0, at t equals 0, I should get 0. And if I take the derivative and I evaluate it at 0, I should get -1. Let's just check that y of 0 equals 0. At 0, cosine is 1 and sine is 0. And we have e to the 0, which is 1. So I would have -5 or -3/5 times 1 minus 6 over 5 times 0 plus 3 over 5 times 1. So I'll have -3 over 5 plus 3 over 5, which is going to be 0. So y of 0 is 0, and I'm not going to check the derivative, but you could take the derivative if you wanted to, plug in 0, and you should get -1 if we've done everything correctly. So that is how we solve problem number 4 in that quiz. And I'll see you next time for the next standard.